Let's now focus on the runtime of our application. Once an FPGA designer has created a final bitstream of the candidate function that he/she wants to be accelerated in hardware, then he/she needs to focus on how to manage the runtime of the application. This step usually requires to write the drivers for the communication with the FPGA accelerators, as well as managing the execution status of the accelerators. To this end, many different approaches are available. A first example involves the instantiation of a soft core on the FPGA logic to manage the flow of data in the execution of the accelerator. In particular, Xilinx provides designers with the possibility to instantiate a soft core called Microbase, which is a 32-bit reduced instruction set computer architecture. Designers can instantiate and tune the processor at different levels. This IP core can be configured to optimize either its area occupation or the performance. Once this IP core is instantiated, it's capable of performing many different operations. In fact, it is designed to allocate memory for the input and output data, as well as managing the execution of the kernel. In these regards, Xilinx Vivado automatically generates the drivers for the communication between the microbase and the kernel. The only thing up to the user is the task to develop a C/C++ code to specify the behavior of the processor. This final task can be performed using the SDK provided by Xilinx. A second example involves the usage of multiprocessor system-on-chip, or MPSoC. These boards are directly equipped with multiple hardwired processors that can be either used bare metal or with the support of an operating system. In such a system, both the processor and the FPGA share the same memory. As described before, here the processors are designed to execute the host code, to manage the creation of data to be fed to the FPGA accelerator and manage its execution. In the high-performance computing scenario, the story is slightly different. In this case, the scenario involves an FPGA device that is connected to the host processor using a communication buffer that is usually identified as the PCI Express. Designers, in this case, need to write the host code of their application as well as all the drivers and IP cores to manage the communication via PCI Express. This task is not trivial. Indeed, in most of the cases, third-party libraries are used. In this regard, SDAccel provides a unique opportunity to leverage a development environment that takes care of all the communication infrastructure in terms of both IP and runtime. The framework, in fact, requires the user to focus only on the kernel design and takes care of all the rest. All the communication over PCI Express is abstracted by OpenCL APIs, and also the execution on the FPGA is managed by such library. This is a huge help in the development of hardware application and FPGAs for high-performance computing. This automatism can be further exploited by third-party softwares that can even increase this level of abstraction to ease the design process. An example of this is the work carried on at the Next Lab at the Politecnico di Milano with the Chaos framework. Chaos is a framework developed in the context of the extra-European project and targets the full stack of the application optimization process, starting from the identification of the kernel function to accelerate, to the optimization of such kernels, and to the generation of the runtime management and the configuration files needed to program the FPGA. Chaos provides the user with multiple ways to program the different FPGA that it is possible to target. However, for some specific FPGAs, it leverages Xilinx SDAccel to generate the binary files for the host and the accelerators. Furthermore, Chaos does not even require an application designer to provide a host code for the application, as it automatically generates the host files and binaries to manage the communication with the FPGA and its memory. Once the host and the kernel binaries have been generated, the only task for the application designer is to execute the host binary providing the kernel binaries, and SDAccel will take care of managing all the runtime and providing benchmarks for the specific kernel.